Imagine walking into a very messy playroom. Toys are scattered everywhere, in every corner. If we sweep it all away and clear the space, we are left with a massive blank floor. This empty floor is waiting for a game. But before we can play, we need a way to describe exactly where things belong on it. Mathematics has a specific tool for this called analytic geometry. You can think of it as a bridge that connects pictures to numbers. It works perfectly because every single spot on our giant playroom floor can be reached and counted simply by taking a few carefully measured steps. Looking at this animation, we can see exactly how this bridge works. A simple drawing of a toy car becomes the number 5. A drawn circle transforms into an algebraic equation. Or if we lose a building block, we can find it just by looking at a short list of numbers. Mathematics gives the picture exact numbers, so it knows precisely where it is. Turning locations into numbers allows us to treat shapes and pictures like mathematical puzzles. This is how engineers track the path of a rocket, by treating the sky like a giant map and calculating every point along its flight. This animated diagram lays down our foundation. A flat floor has 2 different directions, so one number line is no longer enough. We need 2 giant rulers. We place a blue ruler to stretch horizontally, left and right. This is our x-axis. Then we take a red ruler and lay it down, so it crosses the blue one, stretching vertically, straight up and down. This is our y-axis. Still watching our diagram, you can see how to move. First, the character is walking sideways along the blue ruler. Then they move straight up or down along the red ruler, like climbing a ladder. If you mix up horizontal and vertical, you'll end up at the completely wrong spot. Keeping these 2 directions separate allows calculus to measure how fast things change. Right where the blue and red rulers cross, a cozy little toy house appears. The blue ruler has a 0 and the red ruler has a 0, and we lock them together right here. This intersection point is called the origin, and its address is 0, 0. You can think of it as home base. Think of the center square on a tic-tac-toe board, or the start space in a board game. Every other move on the board is counted relative to that home base. You always count your steps starting from this center point. When calculus tackles complex puzzles, it often places them right at this home base to keep the math as simple as possible. Now watch as these crossed rulers glow and project an infinite grid pattern across the entire playroom floor. By crossing the horizontal x-axis and the vertical y-axis, we have created a coordinate plane. Every individual square on this massive grid has its own specific location. You see grids like this all the time. Checkerboards, city street maps, and the square tiles in a bathroom all work the same way. While a physical map stops when it hits the walls of the room, a mathematical coordinate plane goes on forever in every direction. Calculus requires this infinite playground to measure curves of any size. To find our toys on this massive floor, we use a trick called projection. If you take a flashlight and shine it straight down toward our sideways ruler, the shadow shows you the exact horizontal step. Shine it across to the up and down ruler, and the shadow tells you the exact vertical step. This diagram shows exactly how that works. Notice the toy bear sitting perfectly at a grid intersection. When the light hits it, the bear casts a shadow straight down to the number 4 on the horizontal axis. It casts another shadow straight across to the number 3 on the vertical axis. You have to keep the flashlight aimed perfectly straight. As you shine the light diagonally, the shadow lands on the wrong number, and you get lost. Calculus depends on these perfectly straight shadow drops to find the exact area hiding underneath curvy paths. To write down these locations, math uses a password called an ordered pair. It is 2 numbers wrapped in parentheses. The rule for the password is strict. The sideways steps must always come before the up and down steps. This standard order ensures everyone reading the map ends up at the same destination. A password of 3, 5 means taking 3 steps sideways, then 5 steps up. A password of 5, 3 means 5 steps sideways, then only 3 steps up. Swapping that order sends you to a completely different part of the map, and it will break the calculus formulas you'll use later. Looking at this visual, you can see how we label our passwords. The blue horizontal arrow points to the first number. That is the x-coordinate. The red vertical arrow points to the second number. That is the y-coordinate. So in the pair -2, 4, -2 is the x-coordinate telling you to step left, and 4 is the y-coordinate telling you to step up. Textbooks sometimes use older words for these, calling the x-coordinate the abscissa and the y-coordinate the ordinate. They just mean sideways and up-down. In calculus, we are constantly measuring how a tiny change to the x-coordinate causes the y-coordinate to move. Here on our map, the intersecting rulers chop the floor into 4 separate rooms, called quadrants. Starting from the top right corner, we number these rooms 1 through 4 in a counterclockwise circle. In room 1, all your steps are positive. In room 3, on the bottom left, all your steps are negative. We number these counterclockwise to match how circles are measured. When calculus tracks a spinning Ferris wheel, it follows the wheel through these rooms in this exact order. Sometimes a toy sits directly on a ruler. In this diagram, notice that the toy train sits on the horizontal ruler at the number 5. Because it isn't moving up or down at all, its coordinate is 5, 0. Whenever a point has a 0 in its password, it is sitting right on the ruler. A point like 5, 0 lives on the x-axis. A point like 0, 3 lives on the y-axis. Calculus looks for these specific intercepts to figure out exactly where a path crosses the 0 line. We have reached a beautiful two-way relationship. Every single spot on the floor has exactly one password, and every password points to exactly one spot on the floor. Because this match is perfectly reliable, calculus can look at a complicated picture and solve it entirely by doing math with the numbers. Now we can use our map to solve real problems. Imagine 2 toy bears sitting on the floor. They have a pot of honey and they want to share it. We need a reliable rule to find the exact halfway spot between them, so neither bear has to walk further than the other. This animation shows our 2 toy bears. To find the precise middle, we use the midpoint theorem. We take the coordinates of both bears and find the average. Adding their positions together and dividing by 2 gives us the center point. Look closely at the mathematical breakdown to see why this works. We take the blue x-coordinates for both bears, add them up, and chop them in half. Then we take the red y-coordinates, add them up, and chop them in half. Averaging is the most accurate way to find the middle ground. Horizontal and vertical movements are independent. We handle the blue x values first, then the red y values, and never mix them. This process of finding a middle ground on a flat plane becomes essential later, when we need to find the average behavior of a moving object along a curve. A single point is just a dot, but plotting millions of them together allows them to crowd together and hold hands until they form solid shapes and roads. Now, those millions of individual coordinates have become a continuous, looping racetrack. Straight tracks, smiley curves, and winding waves all follow this logic. Every line drawn on this grid is actually a massive family of tiny points, each one obeying a specific mathematical rule. This leads directly into the high-level questions of calculus. Once we use our coordinate plane to build these curvy roads, we can measure how steep the hills are at any single point and calculate exactly how much space fits inside the track. And it all begins with taking 2 numbers and placing a toy on a flat floor.